we're going to do here is, remember, we sort of trailed off here when I got to Gaussian and probability. I tried to stuff a bunch of stuff in at the last minute, and it just didn't quite work because we didn't have time. And so what I did is I went back through and I really expanded that section. So we're going to start at the top of the Gaussian and probability section, and then we're going to march on from there. The entirety of the code I used to create all the figures and all the data for this is available on the website. If you go on there, under the measurements section, under the code, it's a MATLAB M file. So you don't have to worry about the notebook thing, Python, it's just MATLAB all the time. Every day. So we already know how to compute the probability of a value of a random variable x lies in a certain interval from a probability mass function or probability density function. So the sum for a probability mass function, you sum up the bars, or the integral of the PDF, right? The integral is the probability that the random variable takes on a value inside a certain interval, right? You integrate over that region. This means that for sufficiently large sample size, n, such that we can assume from the central limit theorem that the sample means xi are normally distributed, based on the central limit theorem, of course, the probability a sample mean value is in a certain interval is given by integrating the Gaussian PDF, okay? So the central limit theorem told us that the means as a random variable, the sample means, are, if you have large enough samples, they're distributed normally, right? Distributed as a Gaussian. So we can use the Gaussian to compute the probability that a mean will show up in some interval, right? Because we have a PDF and because we know that to compute a probability with a PDF, all we have to do is integrate. So that's the status. The Gaussian PDF for random variable y, representing the sample mean in this case, is, get to there in my notes, is, whoa, fat marker. Gets me every time, fat marker. I feel like it needs like a little theme song. 1 over sigma, which is the population standard deviation, root 2 pi times exp, so e to the negative y minus the population mean squared divided by 2 sigma squared. Sigma squared is the population variance. Okay.
Is that 2 sigma squared or 2 sigma squared?
That is 2 sigma squared.
Okay. Helpful. If not, it's 4 sigma squared. It's different.
That is correct. Okay. The integral of f over some interval is the probability a value will be in that interval. Unfortunately, that integral is uncool. It gives rise to the definition of the error function, which for the Gaussian random variable y is erf, just what you would think, of yb, and we'll talk about what yb is in a moment. It'll become apparent. 1 over root pi times the integral from negative yb to positive yb e to the minus t squared dt. This expresses the probability, a sample mean, probability of a sample mean being in the interval negative yb to yb. If y has 0 mean and variance 1/2. Okay, so we're getting there, right? The error function is defined as this. It's an integral, tells us this probability, but clearly it's not like everything we ever dreamed of, because there are things that have non-zero mean and non-1/2 variance. I mean, so I'm told. So MATLAB has this built in as ERF, shown in figure 4.16. So right here. For positive interval bounds, YB, notice as you increase the interval bound, you increase the error function. It goes up to 1. So as you increase more and more and more of this bound, which goes from negative YB to positive YB, so what you're integrating over more and more, it approaches 1 as you keep going more and more out. Which makes sense, right? Because the integral of a probability distribution, which if you integrate over the entire thing, has to be equal to...
1.
Yeah. Thank you. Whew. He almost embarrassed me in front of the internet. Okay. It's okay, I do it to myself all the time. So, we could deal directly with the error function, but most people don't, and we're weird enough as it is. Instead, people use the Gaussian cumulative distribution function, this capital phi, which is just a function from R to R, which is defined as phi of z equals 1/2 1 plus, you guessed it, ERF of z over square root 2. And which expresses the probability of a Gaussian random variable z with mean 0 and standard deviation 1, taking on a value in the interval -infinity to z. So cumulative distribution functions have this characteristic. They're the probability of a value being taken on all the way from -infinity up to some value. So they integrate from -infinity up to some value of the random variable, and it gives the probability for having anything below that, taking on a value of z or below. And this is really useful to us, but it's not very obvious that it is yet. It's great and all, but occasionally we have Gaussian random variables with non-zero means and non-unity standard deviations. It turns out we can shift any Gaussian random variable by its mean and scale it by its standard deviation to make it have 0 mean and standard deviation, which is nice. We can then use phi and interpret the results as being relative to the mean and standard deviation using phrases like the probability it is within 2 standard deviations of its mean. Okay, that's the type of phrase that we'll be using. The transformed random variable z and its values z are sometimes called the z-score. Okay, so a couple of you have taken statistics before. Yeah, and you guys probably got all up in the z-score, right? All about the z-score. Yeah.
There are tables for this.
Yeah, exactly. And that's what we're gonna look at a table in just a moment.
Oh.
I constructed a table for this, and I thought, how hard could that be? Getting it right was really hard. Getting everything to work out without having like some slightly off aspect to it took a long time, but I did get it, and it was worth it in the end. That's what I tell myself. Okay. So, because I could have used one from the internet, but I was like, no, mine will be better. I would say it's on par. Okay, so
Which course are you on?
which what?
You're on par, yeah, but which course?
Oh yeah, that's true.
Are we confident in that?
Can we get the confidence from the Z-score?
Often wrong, but never in doubt, Jordan. Yeah.
You're gonna be SBS with confidence.
So you win money in poker?
It's also how you lose money in poker, it turns out.
Negative effect?
Okay, so the transformed random variable is called the z-score. For a particular value x of a random variable x, we can compute its z-score, or value z of random variable z, with the formula z equals, you take the value x, you subtract out the mean of x, and you divide it by the standard deviation. So that is the z-score. And compute the probability of x taking on a value within the interval, say, for an instance, x between two values, x b minus, x to b plus from the table. Sample statistics x bar and sx are appropriate when population statistics are unknown. So you can use them in this formula too. These are the population statistics in here, but we could use, if we only know the sample ones, we could use the sample ones. Now, these are, this is really useful. We're going to do an example, so don't worry. For instance, compute the probability of a Gaussian random variable x with, I give you the population mean and the population standard deviation. So the probability, it takes on a value within the interval 3 to 6. Okay? So its mean is 5. So I'm asking you to find the probability it takes on this interval that's not symmetric about that mean. So that's an important thing to notice. So first we compute the z-score of each endpoint of the interval. So let's compute z for the lower bound, so 3 here, equals, so we just plug in what x is, right, which is 3, minus the mean, so I'm just going to write mu x, but it's 5, right? Divided by the standard deviation, which is 2.34, and this comes out to negative 0.85 approximately. And I compute the z-score for the upper bound, equals (6 minus mu x divided by sigma x), and this comes out to be approximately 0.43. So let's think about this for a minute. This is, the mean is 5, so it's closer to 6 than it is to 3, right? So this expresses the difference between the value and the mean. So if we had an interval up to 5, 3 to 5, then one of these z's would be 0, right? This second z would be 0. So it has, it's a measure of closeness to the mean, right? And then it's normalized by the standard deviation. So you can think of this as being the number of standard deviations from the mean. That's what the z-score is, the number of standard deviations from the mean. Okay. Now, we could use, I went ahead and plotted the Gaussian PDF. Boom. And I also shaded it, showing you what the CDF is. So the CDF is the integral of the PDF, right? So you integrate from negative infinity up to ZB. So all the gray area is this line. So it increases from 0, because if you integrate 0, you get 0 out here. And then, oh, the area starts to fill up. We start to see this curve rise. Then it fills up, but it stops increasing quite as fast, and you see this inflection. And then it slowly oozes towards 1, right? So you could actually read what the probabilities are right off of this graph. So negative 0.85 is on this graph. Negative 0.85, I would say, is like here-ish, right? So you go up there and you'd read off the probability that you are less than this negative 0.85 lower bound as being 0.22 or 0.21 or whatever that is, okay? But we can do better than just reading it off of this chart. So what we did is we built a table where it allows us to compute things pretty precisely. So let's go ahead and look up. So the table I give in the table I give in here, and it's one of the appendices. It's Appendix B, the Gaussian distribution table. I'll move it over here. So I repeat these nice charts, these nice plots. But you can also read the values off. So we have negative 0.8, what is it? 0.85. So negative 0.85. So I do... So how you read this is the first decimal is given in this first column, and the second decimal is given so the rows are corresponding to the tens decimal place, and the columns correspond to the hundreds. So if you get negative 0.85, you got to go to this guy. Right? Whoop, that.
Wouldn't that be, that's negative 1.85.
Oh yeah, negative 1.85. Sorry, we were looking at negative 0.85.
Yes.
Yeah, negative 0.85. Very good. So 0.1977 is the probability of being below that, having the random variable be below that lower bound. So Z3 is 0.1977. And the other one is 0.43. Let's look it up. 0.43 6664. I watched Donnie Darko this weekend.
Hey,
Good choice.
0.6664. Yeah, I hadn't seen it. It really aged well. I was kind of worried about rewatching it because I didn't know if I'd still like it, but I really still liked it. So, yeah. Okay. So those are the probability. So the first value is the probability of getting a random variable below this lower bound 3. And the second one is the probability of getting the value lower than the upper bound of 0.66 of 6. So we're almost there. The CDF values correspond to probabilities x less than 3 or x less than 6. Therefore, to find the probability x lies in that interval, we subtract the lower bound probability, right? So the probability of x being an element of the interval 3 to 6 is equal to the probability of x being less than 6 minus the probability of x being less than 3, right? We just want that middle slice. We don't want that tail at the end. We want to subtract off that stuff below the lower bound. So we get, this is approximately equal to 0.66, well, I'll write in, it's equal to phi of 6 minus phi of 3, which is approximately equal to, approximately because it came from a table, 0.6664 minus 0.1977, which is, yeah.
The second one's an exact value.
Yeah,
It's
but
still an
this,
approximation, but
the
it's an exact value
approximation,
of subtraction.
the equality is actually from this. This is approximate. So once it became this, I had to leave it as that. I'm not saying that this is approximately that. What I'm saying is this is approximately that.
Okay.
I know what you mean, though. Yeah. Okay, so there is a 46.89% probability, and therefore, and remember the difference between probability and confidence, not that much, right? So therefore, we have 46.89% confidence that x will be in that interval. Often, we want to go the other way, estimating the symmetric interval xb minus to xb plus, for which there is a given probability. In this case, we first look up the z-score corresponding to a certain probability. For concreteness, given the same population statistics above, let's find the symmetric interval xb minus to xb plus over which we have 90% confidence. Okay? From the table, we want two symmetric z-scores that have CDF value difference of 0.9. So we want 90% confidence, so we have to have the probability of the upper bound minus the probability of the lower bound equals 0.9, right? But there are a lot of values, you could choose two values for which that's true.
As long as they're that same distance apart.
Exactly, but the further constraint that we have it be symmetric adds another constraint, and it is uniquely specified then. So in maths, it's down here. In maths, we have that phi of zb plus, so the upper bound, so the probability of the value lying below the upper bound, minus the probability of the value lying below the lower bound, has to equal 0.9. And the symmetry ZB plus has to equal negative ZB minus. Due to the latter relation and the additional fact that the Gaussian has anti-symmetry, so a Gaussian CDF has anti-symmetry, so it's like if you shifted it down, it would be an odd function, right? It's anti-symmetric. Where is the plot? Right here. So it's anti-symmetric about this point, right? So due to those two facts, we know that phi of ZB plus phi of ZB minus has to equal 1. That is to say, if you were to add the probability of being below the lower bound to the probability of being below the upper bound, you would get 1. And that's, I think that you can tell that that's true if you think like this. So say this was our upper bound, ZB plus, and our lower bound has to be symmetric, right? So this is our lower bound, ZB minus. So what we're saying is if you take ZB plus and you add ZB minus, you're going to get 1. And that's because ZB minus is the probability, so phi of ZB minus. All, that area right there is equal to this area right here, right? That's why it has to equal 1 when you add it. It's the missing piece of the puzzle that completes the CDF. Okay. So now we have 2 equations in phi and 2 unknowns. So why don't we just go ahead and add the 2 equations, because ZB minus falls, phi of ZB minus falls out. Phi of ZB, sort of like Phoebe. Just saying. So adding the 2 phi equations, we get phi of ZB plus equals, we had this plus this is 2 phi ZB plus, right? This plus this is 0. 0.9 plus 1 is 1.9. So we have 1.9, and then on the other side we had a 2, so we divide the 2 over, and we get 0.95. And, of course, since you have to add phi ZB minus to 0.95 to get 1, phi ZB minus is 0.05. So we found those 2. From the table, these correspond with a linear interpolation to this. So let's look those up. So if we look up phi of ZB plus of 0.95, it doesn't matter if we look up the plus side or the minus side because it's symmetric. But so we look up phi of ZB plus equals 0.95. So this table, we got to find in here 0.95, which is in between those 2, right? Now, I just linearly interpolated them. We could probably do better, right? We probably, we can actually use MATLAB, for instance, to evaluate a z-score and all that.
How about you do it and then tell me and I'll verify it?
Yeah, sure. But actually, I don't think MATLAB has an inverse. So I don't think you can look up a probability and have it tell you what the z-score corresponds to. But it would be a fun little program to write, right? You could do a search for it. You could solve for what the z, find the value of the z-score from a given probability. That'd be a fun little function to write. But in any case, we could just look it up in the table, and then we can linearly interpolate because this one lies right in between. So 1.6. So I gotta zoom out a little bit so I can see. 1.64 and 1.65 because it's in between those 2 values. So it's 1.645 1.645. I just linearly interpolated it in my head. It was really hard, I know. You're welcome. All that remains is to solve the z-score formula for x. So in this case, we're going the other way, right? We started with the probability, and we're going back to z, and then we're going to go back to the bound that is on the x variable. So the other time we went from the x variable to the probability. Now we're going probability to the x variable. But we're on the same road. We're just driving the opposite direction. Okay. So solving the z-score formula for x gives us that x, oh, that was large x, x is equal to mu x plus the z-score times phi x. Now, that was just solving, where was that formula? This formula for x. Okay? I believe we can do that. I believe in us. Okay, so from this, we can say that xb plus, so the upper bound, is equal to the mean plus zb plus times sigma x, which is approximately equal to 8.849. That's the upper bound on our x variable for a 90% confidence. The lower bound on our confidence is mu x plus, or sorry, minus z, I guess it's plus because zb minus is negative, right? zb minus sigma x is approximately equal to 1.151. So we have a confidence interval, a 90% confidence interval of 1.151 to 8.849. Okay? And notice that that was larger. We computed the probability of being between this somewhat tighter bound, and it was 40-something%. So if we want to go up to 90% confidence, it makes sense that that range would get larger, that those bounds would move out some. Okay. Now we're going to do an example. The Gaussian confidence for a mean. So consider the data set generated above. So in the last meeting that we had, still the confidence lecture, we generated a data set. Remember that? And we tested the mean value theorem, or the what theorem did we explore? Do you remember what it was called? I was like, we don't trust it. We got to try it out.
Something about a rectangle.
Something about it. Well, we did use the
Central limit theorem.
Yeah, the central limit theorem, but we did use uniform probability distribution, the rectangle. But the central limit theorem was the one that we tested. We said, is the central limit theorem true? Is it true that the means come out normally distributed if you have large enough sample size? And we found out, yeah, it does actually work out that way. So we generated a data set for that. So we're going to use it to do one of these problems. So we want to know what a 95% confidence interval in our estimate of the mean is. So we estimated a mean, right? way back here. Our mu mu, the mean of means, was our best estimate of the mean, and it was 0.4987. And we want to know what our confidence, we want to know the interval over which we're 95% confident in that estimate. Seems like a reasonable thing. And actually, this is like mostly what we care about when we talk about our confidence in a measurement. We want to know how confident we are, usually in a mean value. How confident are we? So, if it is way over here, yeah. So, assuming we have a sufficiently large data set, the distribution of means is approximately Gaussian. Which limit theorem told us that? Central limit theorem, and we didn't trust it, and we demonstrated it to ourselves. Because we're like bootstrap people. We do that. Following the same logic as above, we need a z-score that gives an upper CDF value of 1 plus 0. Instead of 9, this time it's 0.95 divided by 2 equals 0.975. So just up here we computed something very similar, right? We added 0.9 to 1, and we got 1.9, and we divided by 2 and got 0.95. Here we did something very similar, but instead of 0.9, we used 0.95 because we wanted a 95% confidence interval instead of 90% confidence interval. So 0.975 is the CDF value I'm looking for in the table. Let's go ahead and look it up. 0.975, and I believe this one's in there. Bam. So 1.96 is that column? So 1.96. So I define in MATLAB ZB equals 1.96. Okay? Now we can estimate the mean using our sample and mean statistics. So I said you can use sample statistics if you don't have the, and we don't. I mean, for this, we did generate the data, but we're pretending like we didn't generate the data, right? We just have sample statistics. Sometimes it's hard because we're so good that we don't even have to pretend. So, okay. Our estimate of the mean is that it's the mean of means, right? That's our best estimate of the mean, plus or minus some interval ZB times the standard deviation of means, S x bar, the standard deviation of means. Because this value, the mean of means, we know it within a certain confidence based on the standard deviation, not of the samples, but of the mean, right? So this got weird. This is typographically it got messed up, but I think in your notes it should say mu underscore mu plus negative z underscore b comma z underscore b asterisk times SMU. So this is our mean of means that we already computed. Remember when I scrolled back over there, I showed us? Computed the mean of means. Plus, I used this, like, it's not really an interval, it's just a two-value vector in MATLAB, but it represents the lower bound and the upper bound, so it's fine. So minus ZB plus ZB times the standard deviation of the means, so S mu. That's what I needed. And I called that mu x 95, which is our 95% confidence interval in the mean value. Okay, so we have a 95% confidence that the mean is somewhere between 0.45 and 0.54. That's how we interpret this. We say our best guess is that it's mu mu, right? If you had to pick one value where you're saying, like, I think it's going to be closest to mu mu. But if you were to say, okay, give me the interval over which you're 95% confident, you would say, okay, from between 0.45 and 0.54, it's somewhere in there. I have a 95% confidence. Yeah,
But you had to have the mean of the means to calculate this interval.
totally.
So you can't calculate a confidence interval without
Knowing the answer first?
yeah.
So the mean of the means is just our estimate, right? So our mu mu was back here. Our mean of the means was 0.4987. The actual population mean, mu x is equal to 0.5. That was the actual distribution that we used to generate this data. We estimated this to be the mean of means, which is 0.4987. So we're close. And our confidence interval is based on the standard deviation of the means, this value. So mu mu is something that we computed just from the data. We didn't know anything before. We just took the data and we took the mean of each sample and we took the mean of those means. And we got the mean of means, 0.4987, and that's our estimate of the mean, our best estimate. Since we have that best estimate, we want to know essentially how good of an estimate that is. So in order to quantify how good of an estimate that is of the mean, we use its standard deviation and this model of the distribution being Gaussian, right? We're using this Gaussian model of the distribution. So we're assuming that our sample is large enough for it to be Gaussian, right? Because the central limit theorem says that this is only true if you have large samples. So as sample goes to infinity, this is exactly true. It's only approximately true below that. So to summarize, in response to your question, we don't need to know anything about it in order to compute this. Just the data itself. We can just take the data. We just need to assume that we have large enough samples that a Gaussian approximates the mean of or the mean statistics, which is a good approximation when n is like 100 or more. Not as good of an approximation below that. And I don't have them on here, but our next lecture on Wednesday is going to be called Student Confidence. And it's actually what it is there's another distribution that's not Gaussian that's a better approximation of the distribution of the means when you have smaller sample sizes. So Gaussian's great when you have large sample sizes, so we can use this. It's totally valid. But we're going to do something almost exactly the same, but there's a slightly different definition of your distribution that depends on the sample size. It's not Poisson. It's called Student's T distribution.
Oh, okay.
Yeah. So instead of looking up the z-score, we'll look up the t-score. So there's going to be instead of a z table, there's going to be a t table. And they're the same. They're actually identical when you have sample size go to infinity. They converge to each other. But for low sample size, you really should use the t distribution. It's more accurate. So.
For anything under 100.
Sorry.
Couldn't you use it for any value, like even large ones? 'Cause
You can, and it's actually so it is more popular. The Z one is a little nicer because you don't have to take into account the number of your sample size. So your sample size goes into the t table. So we're not only going to have to look it up based on the z score, or the t score, but we're also going to have to look up the probability based on the sample size. And so the table has like another axis to it. It's fun. I haven't generated it yet, but I'll have it generated by Wednesday. But anyways, these are really standard techniques, and I think your homework only requires you to use Gaussian.
One of the problems requires you to use T-square.
Oh, do they?
Yeah, it
Yeah,
does.
more
But
than
the table's
57.
in the book, in
Yeah,
the
there's a-
chapter.
T-square table.
Do you guys want to boldly go where students have gone before?
I mean, for the fact of the matter that if it was due today, the first problem is exactly what we did today. So it's kind of like we definitely couldn't
So
have
the
done it until
last
today.
problem is this one. I mean, it's the T-square.
It's the t score.
Yeah.
So it's like one problem with T-square and then one problem with MATLAB. That's it.
Let's do it. I'll push it. I'll push it one more day. I'll push it to Thursday. I mean, because I do want to make sure we cover all the material before you have the homework due. So.
Yeah. Like my question was honestly on the first question because it uses the table, but it uses it at like you find the number and then it has like a 0.00 up here, and it uses all the values in the 0.00 column, and I was like, how does it know to use those values in the zero column?
Wait, isn't that
It just magically knows.
Okay. You want me to take a look?
Sure.